Hello everyone, let's talk about the following research paper. Automatic prompt selection for large language models. A new and effective method to automatically choose the best prompt for any given input. We will go through the contents step by step. First, we will talk about introduction and then related work, and then automatic prompt selection, a new method. Later, we will talk about experimental setup, and last but not least, results and the discussion. Large language models or LLMs can handle a variety of natural language processing tasks. But creating the best prompts for these tasks is tough and takes a lot of time. Current methods to improve prompts either are not flexible or are not efficient. This is a new effective method to automatically choose the best prompt for any given input. This approach involves three key steps. Step number one, group the training data into clusters and generate candidate prompts for each group using LLM-based prompt generator. Step number two, to create a dataset of input prompt output. Example is to train a prompt evaluator. This evaluator ranks the prompts based on how relevant they are to the input. And the step number three, use the training evaluator to pick the best prompt for new input during testing. This method finds a good balance between general and specific prompts, plus it avoids the need for resource-heavy training and testing. This makes it more efficient. This approach performs well on zero-shot question answering datasets, such as GSM-8K, multi-RF, and AQA. It shows competitive results, proving its effectiveness. In a related work, the first question is, what's the prompt engineering? Prompt engineering optimization of large language models or LLMs through manual or automatic strategies to improve performance across tasks. This field encompasses different strategies, such as prompt tuning, prompt generation, and prompt selection for specific tasks. Prompt tuning, gradient-based search to refine prompts. But it has limitations. For example, it requires access to LLM parameters, which is restricted for some LLMs. And then prompt generation of prompt tokens using optimization techniques. There are two approaches, reinforcement learning and the evaluationary algorithms. This method is efficient and cost-effective by requiring only standard supervised training with offline data. And the prompt selection, the method is identifying high-quality prompts tailored to specific tasks and inputs. For example, auto chain of thought. And it has limitations, for example, high computational costs or latency due to need for LLM outputs for all candidate prompts. The problem statement. Find an optimal prompt generator D for each question Q and the context C to guide the LLM M in producing the correct output A. Here, Q is the question to be answered, and the C, optional additional information related to the question, and Q, instruction added to the original input to guide the LLM. And here you can see the formula for optimization goal, where F is an evaluating function, for example, exact match to the correct answer A. There are some challenges in traditional approach. For example, crafting a new prompt for each sample leads to extensive prompt search space, and multiple iterations of querying LLMs with new prompts make the process cost prohibitive. Proposed solution, the prompt evaluator. Instead of generative model, we will use a prompt evaluator to score the fitness of a prompt P for a given Q and C, iterating over a fixed representative prompt database to select the highest scoring prompt reduces computational costs, and it's efficient. There are three steps. First, prompt database generation. Create a fixed database of representative prompts to be used for different questions and contexts. And second, prompt evaluator training. Train an evaluator to assign scores to topless QCP, indicating the prompt's effectiveness for the given question context input. And third, prompt ranking. Use the trained evaluator to rank prompts from database. Select the prompt with the highest score for the given question and the context. Let's go the steps one by one. Prompt database generation. The key aspects of prompt database generation is similar inputs, question context pairs benefit from the same prompt because they share a common meaning represented in tokens. And there are two steps in database generation. The first, clustering, and the second, meta-prompt generation. And the clustering assign training data, detrain, into coherent groups or clusters, so that inputs in the same group can share the same prompt. For example, we can use the methods encoding or clustering algorithms, and the encoding use the sentence transformer to encode concatenated question and context pairs, and the clustering algorithm apply k-means clustering on the encoded representation to form clusters. And the second meta-prompt generation generate prompts for each cluster using a generative approach. Three methods: meta-prompt creation, generative LLM, and duplicate elimination. Create a meta-prompt by selecting a few question context answer, topless QCA, from each cluster as examples, and then use an additional LLM, for example A1, to generate candidate prompts based on the meta prompt and instructions. Perform an exact match check to remove duplicate prompts, ensuring distinct entries in the database. And there are some advantages of this approach. Compared to manual crafted prompts, this method provides more creative and diverse candidate prompts and automates prompt generation, reducing reliance on human-created prompts. For example, here's the algorithm for prompt database generation. First, initialize the prompt database P and group training data into C clusters. And we will loop through each cluster. For clustering clusters, do randomly construct a set of demonstrations, the demo, to build meta prompt, P meta, and then generate prompts for each meta prompt and return the prompt database. And then in the prompt evaluator training, we will focus on to develop a model called the prompt evaluator E that assigns a relevance score S to a given prompt P based on its relevance to the input question Q and the context C. For example, here you can see the formula, the model definition. Training the prompt evaluator has the two steps: data collection and evaluator training. In the data collection, prepare a comparison dataset to train the evaluator using preference learning. We will form the group for a given question context pair Q and C, and the correct answer A, group related prompts P into good and bad prompts. For example, here is a given formula for good prompts and bad prompts, and lambda is decision threshold, which stands for maximum minus minimum and divided by 2. We will consider only M closest question context pairs to the cluster, centroid, to ensure data representativeness and manageable size. The collection process is automated without human intervention. And the evaluator training train the prompt evaluator to differentiate between good and bad prompts. The process includes training data formation, creates a bipartite combinations of good and bad prompts, sample pairs for each sample QC with the correct answer A, good prompts P good produces answer A prime similar to A, and the bad prompt P bad produces an answer different from A. Here is the high score for good prompts and the low score for bad prompts. There is also given loss function, where E stands for margin, controls the minimum distance between correct and incorrect inputs to reduce noise predictions. And the last but not least, prompt ranking. to select the optimal prompt P for a new input Q prime and C prime by leveraging the prompt evaluator E to rank candidate prompts from the prompt database P. The process includes score calculation, prompt selection, top K prompt selection, and the voting mechanism. In the score calculation, for a new input Q prime and C prime, calculate the relevant score for all candidate prompts P and the prompt database P using the prompt evaluator E. And the prompt selection, we will focus on selecting the prompt P with the highest score. Utilize the top K selected prompt to generate outputs and apply a voting mechanism to ascertain the most common output among the responses generated by these prompts. And the mode of outputs A prime provides a balanced and accurate result, mitigating potential biases and outliers associated with specific prompts. And the prompt with the top K scores defined by this formula. And here we can see the full overview of the process. First is prompt database generation, and the second prompt evaluator training, and the third prompt ranking. As you can see here in the prompt database generation, we have training data and we are clustering, as I mentioned earlier. And then in the prompt evaluator, we are pairing the prompt P with question Q and the context C from the training data. Evaluate the prompts into good prompt and bad prompt. In the prompt ranking, we got the candidate prompt from database and rank. The datasets utilized the research paper as JSM8K with number of problems more than 8K. And the complexity of JSM8K is 2 to 8 steps basic arithmetic operations, with the K features high quality, linguistically diverse, and human created, and the multi-arith is multiple arithmetic operations, reasoning, and the K feature is subset of math piece and tests complex reasoning, and the AQA is complexity algebraic problems, natural language, and the K features includes options and rationales. The models and configurations, all the prompt generation, prompt evaluator utilize the GPT 3.5 Turbo with the temperature 0 and top P1 and maximum tokens 1000. And the training setup for prompt evaluator is using the optimizer Adam with weight decay 0.1, bit size 16, and epoch 30. The K hyperparameters and the clustering is number of clusters 10 and prompts per cluster is 3. And the meta prompt generation number of demonstration per meta prompts is 10 also. In the database and the training sample size, prompt database 30 prompts, 3 prompts per cluster, and 10 clusters. And the synthetic data samples is 3000, 10 examples per cluster, then 10 clusters to 30 prompts. Approximate training costs, for example, total experiments 30 USD, and evaluation on test sets is 10 USD. Here you can see some case study from AQA dataset. There was given a question of the 200 students in a school, at least 45% attended the prompt night and at least 35 took part in the debating session. What is the maximum number of students who could have neither attended the prompt night nor the debating session? And the given options are A 27, B 81, C 90, D 99, and E 1 and 10. The correct answer is E. And there is a prompt, for example, good prompt. Given a mathematical question, the AI should follow these steps to solve it. And here you can see numbered list of requirements. For example, read, understand the question thoroughly, identify the relevant mathematical concepts, organize the given information, solve the equations, and etc. And the bad prompt, there is imagine you are a math teacher and the AI is your student. Your task is to guide the AI to solve the given mathematical problem Begin by highlighting the variables in the problem and their relationship. Then define the formula or equation that suits the problem. And there is answers. For example, the good prompt has answer E and the bad prompt none, while the score is 0.98 for good prompt and 0.05 for the bad prompt. And here also we can see some results. For example, automatic prompt selection with and without voting. When the top K equals to 5, it has the high accuracy in all datasets, and in a QA accuracy on mass reasoning datasets, automatic prompt selection has the highest accuracy on all the datasets, and the automatic prompt selection without clustering in both voting and no voting settings. When the cluster and vote is on, it achieves the higher accuracy in all datasets. Thank you very much for your attention.